Welcome, folks. So excited to see everybody here today through my little webcam here. We're diving right into Unit 2, and we are going to start off by talking about intramolecular forces. That is, what types of forces hold individual atoms together when they form compounds. So we're going to look at this from a variety of different levels. We'll look at covalent compounds, ionic compounds, even metallic compounds, and understand how they bond with one another, their relative strengths, in addition to the different types of intramolecular forces that exist in the wonderful world of chemistry. So let's dive in and get started. So as you can see, we have quite a bit of learning objectives to take a look at today. We're going to talk about electronegativity differences, understand a little bit about bond polarity, differentiate between different types of covalent bonds, understand the concept of ionic and covalent character, differentiate bonds between what bonds together, that is metals and nonmetals and pure nonmetals, understand metallic solids, analyze graphs of potential energy versus distance between atoms, and understand how to evaluate those particular graphs, as well as contrasting the length and strength of covalent bonds. So there's quite a bit we need to get through today, so without further ado, let's get going. So let's talk a little bit about the concept of electronegativity. Electronegativity is simply the tendency of an atom to attract a bonding pair of electrons. Now, if you remember from our last unit, we talked a little bit about this, that atoms that have a smaller atomic radius are going to attract those electrons more than those with a larger atomic radius. So our highest electronegativity, if we're looking at the periodic table, is going to be up and to the right. Now, this is except for noble gases. And again, we can think about this in terms of Coulomb's law about the distance between those bonding pairs of electrons and the nucleus that is attracting them. Now, differences in electronegativity indicate and dictate what type of bond is being formed, whether it is ionic or covalent. You'll see what we mean here in just a second, but in the graph on the right here, you can see quite a few different numerical values for electronegativity. Now, we primarily won't look at the differences between the values. A lot of times what people will do is they'll subtract the differences in electronegativity, they'll look at a chart, and that determines what type of bond is present. And we're going to look at a little bit more of a simplified way of figuring that out. So first off, let's start by talking about covalent bonds, specifically non-polar covalent bonds. Now, when we refer to polarity, we're simply referring to the distribution of electrons. Bonds that are polar are going to have an uneven distribution of electrons, where non-polar covalent bonds are going to have an even distribution or even sharing of that pair of bonding electrons. So non-polar covalent bonds form when electronegativity values are similar. This is characterized by an even sharing of electrons. Now, most of the time, this is going to be an atom that is bonded to the same atom. That is, if you take a look at the diagram on the top right here, a nonpolar covalent bond would exist between two chlorine atoms. They share the same electronegativity, so those pair of bonding electrons that are in the middle there aren't closer to one chlorine than the other. They're right there in the middle, so we call that a nonpolar covalent bond. Now, it's not always necessarily the same atom. So, for example, carbon and hydrogen, the differences in electronegativity are relatively small. So many times chemists will refer to carbon and hydrogen bonds as nonpolar covalent bonds, even though they do have a small difference in electronegativity. Now, polar covalent bonds form when the electronegativity values are different, and this is characterized by an uneven sharing of electrons. The partial negative charge is found on the more electronegative atom that is in the pair. So for example, if we look at the polar covalent bond in the bottom left of the chart there, you see we have hydrogen and chlorine. Well, those valence electrons, or sorry, those bonded electrons are going to be more attracted to the chlorine than the hydrogen, because chlorine has a much higher electronegativity than hydrogen. So those bonded pair of electrons are going to be much closer to the chlorine than they will to the hydrogen. That results in an uneven distribution of electrons, which results in the chlorine being more relatively negative and the hydrogen being more relatively positive. And you'll see how this plays a role in intermolecular forces when we dive into the next unit. But for now, just focus on polar covalent bonds being when we have two atoms where the electronegativity values are significantly different from one another. Now, larger differences in electronegativity result in a larger bond dipole. That is, it's going to be more polar. So if we have even larger electronegativity values, there's not even going to be a sharing of electrons. Rather, it is going to be the taking of an electron. Ionic bonds form when they have the largest differences in electronegativity. So for example, if we look here on the right-hand side, we have an ionic bond, and it is a complete transfer of one or more valence electrons, resulting in full charges. Remember, we talked about polar covalent bonds as having partial charges. That's why you see that lowercase delta sign in front of the positive and negative. It means that there's relative positive and negative charge. But when one electron completely deserts one atom and satisfies the octet rule of another, that is a complete change where the sodium, in this example, loses its electron, thus resulting in an Na with a positive charge, and chlorine with a negative charge. Thus, atoms with a positive charge and a negative charge, think about Coulomb's law, are going to attract one another because they have opposite charges. Now, one thing to keep in mind is that when we talk about covalent versus ionic, it is not just two specific buckets that we put these atoms or molecules in and say this is covalent, this is ionic. All bonds have what we call covalent character or ionic character, and it really is more of a continuum. The more ionic the bond is, the less covalent character it has, and the more covalent character it has, the less ionic it is. So really, it's not just, like I said, two buckets you put them in. It really is a continuum in between. We tend to put them in buckets just because it's simply easier for us as chemists to be able to organize and identify these types of bonds. So in an ionic bond, the difference in electronegativity is so high that one atom just loses that electron and the other one gains it. The electronegativity is so high that basically it takes that electron from the other atom. Now this results in opposite charges on each atom, which now attract one another. Again, just like what we talked about. Now think about it in terms of Coulomb's law. We have a sodium with a positive charge and a chlorine with a negative charge. Well, things that have a positive and negative charge attract one another, and that's when we get our ionic bonds. Now, an easier way to determine bond type, specifically between ionic bonds and covalent bonds, is looking at what constituent atoms they are made of. So, for example, most ionic bonds you find are going to be metals and nonmetals that are bonded together, while covalent bonds are going to be nonmetals and nonmetals bonded together. So if it's unknown, let's say we can't determine the type of bond that is present, we can actually determine it from its chemical properties, which we'll dive in when we start talking about types of solids a little bit later on in this unit. But the big thing to take home here is that we can differentiate ionic and covalent bonds based on the constituent atoms that they are made of. Metals and nonmetals make up ionic bonds, while covalent bonds are typically solely just nonmetals and nonmetals. So let's explore what types of bonds we might find between the following. We have Cu and Cl, C and F, and N and N. Well, if I look at Cu and Cl, Cu, copper, is a metal and chlorine is a nonmetal, so I can safely say that that is probably going to be an ionic bond. C and F and N are all nonmetals, so those are primarily going to be covalent bonds. Specifically C and F, because they are two different atoms, are most likely going to be a polar covalent bond, where the two nitrogens are going to be a nonpolar covalent bond because nitrogen and nitrogen are going to have the same electronegativity values. And you can see those answers are absolutely correct, as if I would ever get anything wrong. But the idea here, just make sure you can identify different types of bonds based on the individual constituent atoms that they are made of. Now, metallic bonding works a little bit differently. These occurs between atoms of metals. Now, the valence electrons in these are considered delocalized, meaning that they are free to move throughout and not really attached to any one particular atom. So those electrons, rather than being just associated with one particular atom of the metal, are able to kind of flow freely through the metallic solid. Well, that helps us understand a really important concept with metals, and it's the fact that they can conduct electricity. And that is due to the fact that the electrons are free flowing within the metal. So as a result, if we were to take flows of electrons, which basically what electricity is it's a stream of electrons, and we flow that through the metal, it will easily go through. Whereas if we try to do that with covalent and ionic bonds, well, the electrons that exist within covalent and ionic bonds are stuck in that bond. They cannot flow freely through the covalent or ionic solid. So as a result, they don't conduct electricity very well. But metallic bonding can, again, because those valence electrons are delocalized. They're not specific to one particular atom of the metal itself. So let's talk about the strengths of the bonds. Now, covalent bonding, we can have single bonds where it just shares one pair of electrons, double bonds where we share two pairs of electrons, and triple bonds where we share three pairs of electrons. So it really makes sense to think that the more electrons that are shared between the two individual atoms, the stronger the bond is. And that is the case. The strength of the bond increases as we increase the number of bonds that are present. So single bonds are going to be weaker than double or triple bonds. This also results in triple bonds being shorter than double or single bonds. Again, stronger attraction, right? The closer they're going to be to one another. Again, same concept, Coulomb's law. The stronger the attraction, the closer those atoms are going to be together. So as the strength of the bond increases, the length between the two individual atoms decreases. So a triple bond is going to be shorter than a double bond, which will be shorter than a single bond. Now, ionic bond strength is determined by two major properties, and again, goes back to what we've talked about previously. The atomic radius of the atom itself, as well as the magnitude of the charge, whether it's a +1, +2, +3 charge. And that goes back to Coulomb's law. So utilizing these factors, we can determine the strength of the bonds, as well as their relative length. So let's take a look at this graph here. This graph is really important because it helps us understand a little bit about how atoms form bonds. A graph of potential energy versus distance provides us lots of details about bonding. Now, when a bond is formed, the reason that atoms form bonds is because it results in them having very low potential energy, which is what makes them so stable. If we have lower amounts of potential energy, we're stable. We don't have as much energy to be able to do work, so we're quite content just being happily bonded to one another, like in a happy marriage. Learn what that's like one day. It sounds really negative. I apologize. The lowest potential energy is where the bonds form. If the atoms are too close to one another, you think about it, we get those nuclei really, really close to each other, they're going to repel, right? The two positively charged nuclei get really close together, they repel one another. If the atoms are too far apart, there's not going to be any valence electron attraction from one atom to another and vice versa, but there's this kind of like this Goldilocks zone here, where it's not too far away, not too close, but it's just right where those atoms are going to bond. Now that's going to, again, depend on the radius of the atom as well as the number of bonds that are present. And we'll see that as we take a look here. But if you look at the graph here on the right, you can see that the perfect internuclear difference is 0.74 picometers. And you can see that the lowest potential energy is there. Again, that is the perfect distance where we get the most amount of attraction and the lowest amount of potential energy. So that's where we're going to find the greatest stability of the bond between these two individual atoms. So consider the impacts of atomic radius. Stronger bonds are going to be indicative of lower potential energy. So if you see we have a single bond here, if we had a double bond, well, that's going to result in the dip being greater because we're going to have lower potential energy. That bond is stronger, therefore it is more stable, and therefore it has lower potential energy than, say, a single bond. We can also think about that in terms of bond length as well. If we have a double bond or a triple bond, the bond length is going to be shorter, so the internuclear distance is going to be smaller. So we need to think about shifts in this graph based on whether the bond is stronger or weaker than what we've looked at. So let's summarize and see what that looks like. Atoms with a combined larger atomic radius will have internuclear distance that is larger than smaller atoms. So what that means is that if we have a larger internuclear distance, we're going to shift to the right on that graph because the bond length is going to be larger. In addition, this also results in the potential energy dip to be smaller due to less attraction due to Coulomb's law. If those atoms are bonded, but they bonded a further distance away from one another, then that attraction is going to be smaller. And so therefore the potential energy dip is going to be smaller than that of what you see here. So if this chart represented F2, what would differ in a molecule that is Cl2? So there are two things that we need to consider here. First off, if we know and can draw our Lewis dot structures, we know that F2 as well as Cl2 are single bonded to one another. So we really can't take that into consideration, but what we can do is take into consideration the atomic radius. The atomic radius of fluorine, higher up and to the right, is going to be smaller than that of chlorine. So as a result, chlorine is going to have, Cl2 rather, is going to have a larger atomic radius, thus the graph would shift to the right for a larger internuclear distance. Furthermore, the dip in the graph is going to be smaller because the larger radius indicates less attraction due to Coulomb's law. The individual atoms are further away because the atomic radius of chlorine is larger, and therefore they're going to form a bond at a bond length that is going to be greater. So as a result, we get a shift to the right. Furthermore, in addition to that, the bond energy is going to be less because, again, there's less attraction due to the radius, the distance between them, the bond length being larger. So there's quite a few things we need to consider when we look at potential energy versus distance graphs. But again, just like what we've talked about over the last 2 units, if you think about these things in terms of Coulomb's law, it becomes much, much easier to not only understand these graphs, but to explain and justify why there are changes within the graph. And that's primarily what we're looking for at this stage. So again, we've covered a lot of different topics here, but the main goals here are being able to differentiate between the different types of bonds. Furthermore, also being able to understand that potential energy graph versus internuclear distance. So hopefully you've got a good understanding of that. We'll talk more about this in class. Hope everybody has a great day, and we will see you soon. See ya.